Today we're going to be going over domain and range. So we're going to go over what is it, the notation, and also continuities and discontinuities, and how to write these using notation from domain and range. So what is domain and range? Domain and range apply to relationships between numbers, and today we're going to be focusing on a special kind of relationship, and these are functions. So we're going to be talking about domain and range as it applies to functions. A function is a special type of relationship when every input has exactly one output. So think of it kind of like a machine, where you can put in exactly one input into the machine and you get out one output. When we're talking about domain and range, we are referring to these inputs and these outputs. So for domain, the domain is the set of all possible inputs that you can put into the machine. So in this case, we're talking about all possible x values that you can plug into this machine. And the range is the set of all possible outputs. And in this case, it's all possible y values that we get out of this machine. Okay, for example, if we had a function where it was f of x equals x plus 10. So this x represents all the inputs that we can put in. For example, we could put in something like 1, and it'll be f of 1 equals 1 plus 10, and it'll give us an output, which is 11. You could also put really big or really small numbers, and let's say we put in 100. So f of 100 is equal to 100 plus 10, and the output it gives us is 110. So the numbers that we've just put in, all of these x values are possible inputs. We are able to put it into the machine and it'll give us the correct output. That's what the domain is referring to. It's referring to all the set of numbers that you can put into the machine and it'll give us a value that works. Now, this isn't the case all the time. Some numbers just don't fit inside a function, and we can call these numbers domain busters. Now, let's give you some examples. For example, let's say we had f of x is equal to the square root of x. Now, for this function, you can plug in all sorts of numbers, and let's just say we plugged in 4. So we have f of 4 is equal to the square root of 4, which is 2. Now, let's say we plugged in 36, and we'll have f of 36 is equal to the square root of 36, which is 6. Now, let's say we were to plug in a negative number. Okay, let's say we have f of negative 1, and we get square root of negative 1. Well, we can't take the square root of a negative number and have it result in a real number. And in this case, since we're talking about real numbers, this wouldn't fit the function, and this will kind of break the machine. So for this function, the domain is all positive numbers, since negative numbers don't fit. Let's take a look at a different domain buster. And for this example, we're going to be talking about division by 0. So let's say we had a function f of x equals, let's do 1 divided by x. Now, for this function, again, you can put in a bunch of different numbers as the input. Let's say we have f of 1, and that'll equal 1 over 1, and you can put like f of 2,574, and you'll have 1 over 2,574. You can put in a bunch of numbers, and in this case, you could even put in negative, so we could have negative 1, and this would be 1 over negative 1, which is just negative 1. The only number that we can't put in here is 0, because you can't divide by 0. So in this case, if we were to put 0 into this function, this machine will sort of break, because this will be undefined. So for this function, the domain is all real numbers except for 0, because you can't put 0 in. Let's take a look at another example. Let's say we have the function f of x equals log of x minus 1. So, for logarithms, the rule is that you can't take the log of 0 or a negative number. So any x that makes you take a log makes the inside of this into 0 or a negative number is a domain buster. Now, what numbers could that be? Let's say you were to plug in the number 2. So you have f of 2 equals log 2 minus 1, and you'll get f of 2 equals log of 1. And now you can take the log of 1. Now let's say you plugged in 1 instead of 2. You have f of 1 equals log 1 minus 1, which is the same as the log of 0, which is undefined. You can't take that. Let's imagine that we plug in any number that is less than 1. So let's say we plug in 0.5. So we'll have f of 0.5 is equal to log of 0.5 minus 1. And now this will result in the log of negative 0.5, which is a negative number. So this wouldn't fit into the domain. So from this we can come up with the rule, and that is, since we can't put in x that makes us take the log of 0 or a negative number, we can only put in an x that is greater than 1. So the domain for this equation or this function is any x that is greater than 1. Alright, let's look at the range of different graphs. Let's say we have the equation y equals x. So this graph will look something like this. We have a y-axis and we have an x-axis, and the line goes through the origin diagonally. Now, since we established that the range is just all the possible output values or all the possible y values that we can obtain from a function, we can see that the range for this graph, since it covers and it goes through the entire length of the y-axis, and it also continues on to infinity without stopping, we can say that the range is from negative infinity to infinity, so the range is basically all real numbers. Similarly, if we're going to look at the domain of this graph, we can see that this graph right here goes through all the possible x values here, since this graph covers all of them. So in this case, the domain is also all real numbers. Let's take a look at another graph. Let's just say that for this graph, it looks something like this. Alright? And this top point right here is at a y value of 2. Now, this graph goes and extends all the way to negative infinity for the y values, but when you follow this graph up, it stops at this point, and no other y values are represented up here. So, for this graph, the range would be all negative values starting from negative infinity, and it goes into the positive, then it stops at 2. So the range here would be from negative infinity, and it goes up into 2. Alright, let's talk about notation, or how you write and describe these domain and ranges. Now, there are multiple ways of doing this, and today we're going to be going over the inequality method and the interval notation. So for the inequality methods, what you're basically doing is describing the possible x values using inequality signs. For example, you could use greater than, less than, greater than, equal to, less than, equal to, or not equal to. For example, if the range of something was from negative infinity all the way up to 2, but not including 2, you would write it as something like this. The range would be, since it's negative infinity and it goes to 2 but not includes it, it would be, the x would have to be less than 2, since this includes everything from negative infinity all the way to, let's say, 1.999, but it doesn't include 2. Another example, let's use the function we used before, which is f of x is equal to 1 over x. And we've established before that you can't plug in 0 here, or else you'll be dividing by 0, which is undefined. But every other number works for this function. So in this case, you could describe the domain like this. You could say that the domain is all real numbers, but the x cannot equal 0. Now there is a shorthand way of writing x is equal to all real numbers, and it's this. So instead of writing out this all the time, you could just go for the domain x and then this capital R symbol for all real numbers. So in this kind of almost E-like symbol is just, this means that x is an element of, which basically means that x is part of the set that's represented by this R symbol. Capital R in Latin just means all real numbers. So this is a shorthand way of writing all real numbers instead of having to write out the entire sentence. Let's talk about the interval notation. So, like the name suggests, the interval notation, we're just going to be describing the domain in intervals. So we're going to be primarily using the symbols bracket, the straight bracket, and the regular parentheses. What interval notation looks like is, let's say you had all real numbers. Let's say you have a function like y equals x, which looks like this. And since the domain is all real numbers, you could write it like this. You would put a parentheses, and you'll say, okay, so where does this start? So we know that it starts from negative infinity, and it goes all the way to infinity. So the domain covers this entire portion. So we'll say, okay, so on the left, it starts from negative infinity, and it goes to, so this comma separates the start point, and this is the end point. So it goes from negative infinity all the way to infinity. Now, for the infinity symbol, you'll always want to use the parentheses, because what this parentheses represents is that you start at that number, but you don't include it. So if you had, let's say you had a parentheses here, so you start at 5, and the domain goes from 5 all the way to 10, and you stop. What this parentheses means is that it starts at 5, but it does not include 5. So for this domain set, it'll start from like 5.1111, but it will not include the 5. Now, if this 10 was a square bracket, this means that it goes up to 10 and it includes 10. So interval notation and inequality notation are interchangeable. You can write domain or range using both. For example, if you had the inequality the domain x has to be greater than 5, you could write this the same way using interval notation by saying, okay, since x is greater than 5, we're going to be starting at 5, and notice how this is a greater than and not a greater than equal to, so 5 isn't included. So it'll go from 5, and since it's greater than 5, it'll go all the way up to infinity, and it'll stop there. And let's say we had x is greater than equal to 0. So in this case, since x is greater than or equal to 0, and we're including 0, we'll need a bracket here, and the start point is the 0, separated with a comma, and the end point is positive infinity, because all numbers that are greater than 0 would fit into the domain. And now let's say we have the range, and the range in interval notation would be 3, 7. So we're going to be going from 3 all the way to 7, and we're leaving out anything else. So for the inequality notation, we're going to be, our range, which is y, has to be less than 7 and greater than 3. So we'll write it as, it has to be less than 7 here, but it has to be greater than 3. So this would be the notation using inequality. So This side would be inequality, and this side is interval notation. And it goes kind of like that. Alright, let's talk about continuities and discontinuities. So what these are referring to is, does the function break anywhere? For example, a continuous function would be something like the function y equals x, where the function is just a straight line that never breaks, and a discontinuous function would be the function like f of x is equal to 1 over x, where the function breaks in the middle. Another way to think about this is, for continuous functions, can you draw the function without lifting your pencil off the paper? And for this first function here, you can, because you just go from the bottom side and go all the way to the top, and that would be your function. But for f of x equals 1 over x, you can't draw it without lifting your pencil, because if you go here, you'll have to lift your pencil up to draw the top part here. So there are three different types of discontinuities. We have point, we have a jump discontinuity, and we have an asymptote. A point discontinuity is where only a single part of the line of the function is broken. So let's say we have a function like this, but there's this point here missing, and then it continues. So that would be a point discontinuity. And for jump, it's as if someone just removed a piece of the function and brought it either up or down. So an example, let's say the function were horizontal, and then once it reaches this point, it stops, and then it continues off higher up, and then it continues. And for an asymptote, let's use a familiar example. We'll use 1 over x. So an asymptote is a discontinuity where there's this point, or there's this value where the graph is always getting closer to, but it never touches. Alright, so let's talk domain and range for these discontinuities. So first of all, let's use a different color here. So let's start with the point discontinuity. So for this, let's say the point was at a y value of 2 and the x value of, let's say, 4. So if we were to look at the domain, which is all possible x values that this graph has, it goes from negative infinity on this side, and it keeps going all the way until 4, but it doesn't include 4, and then it goes all the way to infinity. So the way to write the domain here, let's use the interval notation. So the interval notation would be, we're going to be starting from negative infinity. We're going to be going into 4. And since we don't include the 4, we're putting in parentheses. We're going to draw a union symbol. And we're going to start off at 4 again. And we're going to go all the way to infinity. Now, let's do the inequality notation. So for this notation, it'll be x is equal to, or is an element of, all real numbers except x cannot equal 4, because every other value works just for except for 4. Now let's look at the range. So for this point discontinuity, the range goes from, let's say this number here, the minimum point, let's say this number is negative 3. So for this range, we're going to look from bottom to top. So bottom to top. So this range starts at negative 3, and it includes negative 3 because that's the point here. So it includes negative 3, and it goes all the way up and stretches into infinity. So if we're going to write if we're going to write the range in interval notation, they'll look like this. We'll put a bracket because it includes -3, and it stretches all the way up to infinity, so that would be our notation. For the inequality notation, we're going to use y instead of x because we're talking about range values, and the y value has to be greater than or equal to -3. So that's that for the point discontinuity. Let's look at the domain and range for the jump discontinuities. Let's say this is at 2, and let's say, let me make this function extend to infinity. Okay, so, and let's also say that this y value right here is also 2, and that this y value where this dot is, let's say this is 4. So let's look at the domain first. The domain for this is -infinity, so it goes from this side and it goes all the way to 2. But even though that there's a break vertically here, notice that there is no horizontal break, because even though this is an open circle, the function fills it in up here. So in this case, the domain is actually -infinity all the way to +infinity because there's no break on the x-axis. So the domain would be -infinity all the way to infinity, and in another notation, we could also write it as x is equal to all real numbers. So let's talk about the range. Now for the range of this graph, this is kind of tricky, because for this, the range is only the values 2 and 4, because these are horizontal segments. So for this range, you could just write it as the y is equal to 2 and the y is equal to 4. And that's about it. Alright, let's look at the last graph right here. So, for this graph, we can see that for the domain of this graph, we can see that we're going from -infinity all the way to 0, then from 0 all the way to infinity. So we can write that as -infinity to 0, union sign to connect the two, and then 0 to +infinity. And we can write this in interval notation, inequality notation, by saying that x is equal to all real numbers, but x cannot equal 0. For this graph, the range is similar. We're going from -infinity, going from down to up. There's also an asymptote here horizontally. So we're going from -infinity, we're stopping, on color. We're going -infinity, we're going up, we're stopping at 0, then we're going to continue going up to +infinity. So the range is the same, -infinity, 0, union, 0, +infinity. So in summary, the domain is the set of all possible and valid x values that you can put into a function, and the range is the set of all possible y values that the function is going to give you, or all possible outputs. And remember to always use proper notation when you're describing domain and range. And that'll be all.